Hello, welcome back to the course on Interpretable and Explainable Machine Learning. In this lecture, I will define the general framework and the terminology that we will use in the rest of this course. The primary goal of this lecture is to define the essential machine learning vocabulary that will appear in the rest of this course. A secondary goal will be to identify what interpretable and non-interpretable features are. The general setting is that we start from a specific machine learning problem, and in this course we will focus on the case of supervised learning. This setting is illustrated here in this figure, which I introduced in the first lecture. On the left, we have the training dataset that consists of input and output pairs, for example images and the corresponding category labels. We use this dataset to train a model, illustrated in the middle here as a black box. The goal is to train the model to predict outputs from inputs, and this is done by automatically adjusting parameters in the model, and the parameters are illustrated here in red. Finally, we test how well the model predicts the output for new test inputs, and this is illustrated on the right of the figure. The goal of this lecture is to define the different terms that appear in this illustration, and specifically what a dataset looks like, what a model is, and what it means to train and test a model. So let's start with the dataset. A dataset consists of a set of inputs, shown here on the left, and the set of corresponding outputs, shown on the right. In this course, we will be representing the set of inputs as a matrix X, where each row, illustrated in orange, is one data point. Each row is also called an instance, and the matrix collects a total of n instances. Each instance of the input consists of a set of values of different features of the input. So each column in the matrix, illustrated in blue, collects the values of a given feature over instances. And we will have a total of p features for each instance. So the ij entry of the data matrix X is the value of feature j in the instance I of the input. And the output is going to be a vector, shown on the right here, where entry I corresponds to the output to the instance I of the input. Let's look at one of the examples I introduced in the very first lecture, intensive care prediction. Here, we are considering a situation where a patient comes to the emergency room of a hospital, and the goal is to determine whether this patient should be admitted to intensive care or not. And a machine learning model is trained for this on previously collected data. In this case, each data point, each instance, is a previously treated patient. And the different features of the inputs are the characteristics of the patient based on their medical history, for example, the presence of chronic diseases, and physical examination findings, such as, for example, blood pressure. The output is whether this previously treated patient survived hospitalization or not. A second example is pneumonia prediction from chest radiographs. In this case, each instance in the dataset is a radiograph of a patient. The individual features of the instance are pixel values for each pixel. So now each column in our input matrix is going to be the value of one given pixel. And the output for each instance is whether pneumonia was present or absent in this patient. Note that in this course we will focus on data presented in terms of such matrices. This is called tabular data. It is important to take into account that data can come in other formats, such as text or graphs, but we will not focus on these formats in this course. Going back to the general setting, so far I've described the format of the data. We will next turn to the model. What is a model? A model is a function or program that takes as an input one instance, so a vector of values for p features, and then maps this input into an output, which is also called the prediction of the model. In general, the model depends on a set of internal parameters that are collected in a vector called theta. And this set of parameters is adjusted by training the model. What does it mean to train the model? It means to adjust the parameter values in such a way as to minimize a cost function, which is evaluated on a subset of data called the training set. So training or learning is an optimization of a cost function, which is often also called a loss function. There are different types of possible loss functions. A very common example is the mean squared error. It consists of the difference between the model prediction for a given training instance and the actual output of this instance, which is then squared and summed over all instances in the training set. This is the general setting. Then there's additional terminology that depends on the specific format of the variables. There are in general two types of features. Features with continuous values, such as blood pressure, and such continuous features are often also called quantitative features. The second type of features are features with discrete values, such as, for example, whether a patient has asthma or not, and such discrete features are usually called categorical or qualitative. Similarly, the outputs can be either continuous or discrete. If the outputs are continuous, the prediction problem is called a regression. If the outputs are discrete, the prediction problem is called a classification or categorization. Finally, discrete variables, inputs or outputs, can be coded in several ways. One very common type of encoding is what is called one-hot encoding, or equivalently an indicator variable. This is a type of encoding where we have one binary variable, 0, 1, for each possible category. The terminology I covered so far is common to all of machine learning. In addition, there is some terminology that is specific to explainable machine learning. Most importantly, the different features of an instance can be either interpretable or non-interpretable. An interpretable feature is a feature that has an immediate interpretation for the studied problem. For example, whether a patient has asthma or not, what is the height of a person, or what is the size of an apartment if we want to predict its price. Non-interpretable features are features that correspond to raw data, such as the value of a pixel in the image or an amplitude of a sound wave. In general, if the dataset consists of interpretable features, it is called structured data. If it consists of non-interpretable features, it's usually called unstructured data. And within explainable machine learning, these two different types of data require different methods. As for unstructured data, we first need to identify interpretable features. This brings me to the end of this lecture, in which I introduced the general terminology that will be used in the rest of this course. Don't hesitate to come back to this recording later if needed. See you in the next lecture.